All right, physicists, welcome to another class, another month, new month. All right, new month, new way of talking about physics. For the first half of this unit, we were talking about forces and doing everything with F equals ma. Okay, so when we were doing that, we would write down F equals ma. We would draw all of the forces on an object. So for instance, we might draw the normal force, the gravitational force, and the force of tension. And then what we would do, we would say F equals ma applies in every direction. You would go ahead and find what your net force is. That would give you your acceleration in meters per second squared. Remember, force is in newtons. And once we know our acceleration, then we can use expressions like use our constant acceleration model to solve for the motion of the object. Okay, that is the old style. Now we're moving into a new style of talking about problems. And in our new style, we are going to try to simplify things. And the reason it's a little bit simpler is that in all of this talk about forces, we had to be very, very specific about forces applying to a specific direction. And then we would keep track of the speed in every single direction. On the other hand, in this way of talking about things where we're talking about the energy of a particle and talking about how much energy we put in or out, the kinetic energy, for instance, notice it depends on the mass of the particle and v squared. V squared doesn't really depend on what direction it's going. Okay, so this is kilograms times meters squared over second squared. Another way to write that unit, kilograms meters squared over second squared, is as a Newton meter, which in fact, so if you're looking at the base units, that's kilograms. A Newton is kilograms meters over second squared, and so now we have meters squared over second squared. But as this Newton times a meter should give us, this is a force times a distance. And what we showed last time with the work-energy theorem is that the amount of work that you do on an object is how much energy is added to it. So if you have a certain amount of kinetic energy at the beginning, you do some work on the object, you end up with a different amount of kinetic energy at the end. So in this drawing, the old way we would have talked about this situation, we have a wire and a bead on that wire, and let's say that the bead is sliding along and we want to speed it up. And we pull on that bead, providing that force causes it to accelerate. The acceleration causes it to go faster, and after some distance where that force has been applied, our particle continues to slide along going faster. Okay, and of course Newton's first law tells us that things that have some speed, you don't have to explain why they continue going at that speed. You would need to explain, for instance, if that bead starts slowing down, then you'd have to start invoking frictional forces and stuff like that. So that was the old way with this F equals ma. Our new way of talking about it is this bead is going along. It has some initial kinetic energy, 1/2 mv squared. Then we pull on it for a while, and what that force times the distance does is that it adds energy. You're doing work on that particle, and it makes it, at the end of the day, go faster. Okay, so just to say it again, what we're doing now is we're redescribing things that we've already done. But this kind of redescription is going to allow us to capture new effects, like later on, heat. Okay, so here's an example that's sort of interesting in the sense that it contains some information that might put you on the wrong track. In class today, I explained the idea of flarf. And this was the idea that in World War II, planes that had to deal with the existence of radar for the first time, what they would do is they would drop out a bunch of tinfoil and stuff like this to try to confuse the radar system, so they wouldn't be able to just say, "Oh, there's the plane, there it is," bam. So throwing all that flarf out, throwing the extra tinfoil out of the bottom of the plane would confuse the radar system. The way I use that term flarf is that there's a lot of stuff that's often presented to you as being important that has nothing to do with the essence of the matter at hand. I feel like this is continually present in politics, where somebody will try to tell you about something that seems important, but it's a distraction. In physics, a lot of your homework problems have the same thing. So let's read the problem and try to identify the flarf and then get our answer. So this is a homework problem. The only force acting on a 2 kilogram canister. So we know the mass of our object is 2 kilograms. That is moving in the XY plane, has a magnitude of 5 newtons. Okay, so I haven't been told a whole lot about this force. It could be in any direction. I don't know what direction. The canister initially has a velocity of 4 meters per second in the positive x direction. Okay, so your initial speed is 4.0 meters per second in the plus x direction. Okay, so I guess I can write that as an I hat or something like that. There, now it's a vector. And sometime later has a velocity of 6 meters per second in the positive y direction. Okay, so there's your v final is 6 meters per second in the positive y direction. So let's write that as a j hat. How much work is done on the canister by the 5 Newton force during this time? Okay, now, the way the problem is written, it makes it seem like this 5 newtons, it makes it seem like that's very important. But really, all it's asking you about is how much work is done. Well, look at this. If you know the initial kinetic energy, or the final kinetic energy, 1/2 m v final squared, and you know what the initial kinetic energy is, 1/2 v m v initial squared, you know that the way that you change that initial kinetic energy to that final kinetic energy is by putting in some work. And that's really all this question is asking. It says, find this. You know m, you know v final, you know v initial. So you can calculate this number, you can calculate this number, you can find the work. That work has to be positive because you've gone from a slower speed to a faster speed. So you're putting in some positive work, but the details of how that force was applied, we don't know about it. And in fact, in this problem, we don't need to know. That's FLARF. Okay? So that problem, I think, if you just saw it on your own, it might be a struggle, but try to think, conceptually on some of these, and they clean up a little bit. Okay, so forces can either help you speed up or help you to slow down. Okay, and the way that we talk about it in physics is that force times distance. If that force is causing you to speed up, we consider that as positive work. If the force causes you to slow down, we call that negative work. So here's a picture where an object is thrown upward, but the force of gravity is pulling down on it. Okay, so that force is acting over some distance as the rock goes upward, and the kinetic energy at the beginning it's going fast, at the end it's going slower. So we say that the force times the distance, the force is going in this direction, the displacement is going in that direction. So if you just use this formula in a straightforward way, you would have F times D times cosine of 180. This is minus 1. Okay? So for this case, the reason why you have negative work is that the force is going against the direction of the displacement. Now, the tricky thing is that you don't want to get the idea that gravity always gives you a negative, does negative work. If your object is going downward, gravity will do positive work. Why? Because in this case, if the object is coming downward, that theta would be 0, and cosine of theta would be, cosine of 0 is just 1. Okay, but just thinking physically about it again, it makes sense because this work is the thing that's causing your speed to change. So if you're pushing on something in the direction that it's already going, you cause it to get faster. That's positive work. If something's coming towards you and you start pushing on it in the opposite direction that it's going, it gets slower. So that counts as negative work. All right, so there's nothing paradoxical about this. It's just a way of keeping track of what we mean. Okay, so for instance, here's an example. It says Kevin is refinishing his rusty wheelbarrow. He moves his sandpaper back and forth 45 times over a rusty area, each time moving a total distance of 0.15 meters. Okay, so he goes 45 times, and each time he goes 0.15 meters. That's the total displacement of that sandpaper. The coefficient of friction for the metal sandpaper interface is 1.8. Okay, sorry. The normal force is 1.8 newtons, and the coefficient of friction is 0.92. The question being asked is how much work is done by the kinetic frictional force during the sanding process. Now, as Kevin is refinishing that wheelbarrow, what's happening is that he is pushing one way. The F of Kevin is going one way, and the F of friction is going the other way. Essentially, if you look at the total work that's done here, well, at the beginning, the sandpaper is at rest. At the end, the sandpaper is at rest. So what's happening here is essentially that Kevin is putting in a positive work, and the friction is taking out a negative work. So if we find out what work Kevin is doing on that, which is essentially going to be, it's going to be some force times F Kevin times the distance, which we have right there. Well, the force that Kevin is applying is essentially just enough to counteract that frictional force, so it's going to be force of friction, which is mu times the normal force. So mu times Fn times d. And you should get something around a plus 12 for the work that Kevin is doing. And then the frictional force is doing negative work, so it is taking energy out there. Where is that energy going, you might ask? Well, I encourage you to go ahead and rub your hands. What happens when you're rubbing your hands? Well, you can feel it. What's happening is that heat is being generated. So instead of the motion of your big, your big meat cakes here, you have the motion of the microscopic particles in your hand, which we interpret as being heat. Okay? So that's a little bit of a hard example. Let's do one that's a little bit hopefully clearer. In this case, we have a helicopter. There's an astronaut who's on the ground, or I guess on the water, who's going to be picked up by a helicopter. And she weighs 72 kilograms. And the helicopter is 15 meters up. Okay, so she's going to be pulled by some force in that direction. And we're given the acceleration, which is g over 10. Okay, so g is around 10 meters per second squared. So essentially, every second as she goes up, she's getting about 1 meter per second faster. The question asks, how much work is done on the astronaut by A, the force of the helicopter, B, the gravitational force on her? Okay, now, let's think about it. If we wanted to find out the work, we're going to have to take the force times the distance times the angle, the cosine of the angle, rather. But if we have F net equals m times A, we can write m times A, so we know her mass, we know her acceleration, which is g over 10, equals what forces are acting on her? Well, there's some tension force pulling up, presumably a little bit bigger than the force of gravity pulling down. So the force of gravity we already know, the Fg is going to be equal to 72 m times 9.8 newtons per kilogram. Okay, so that's the force of gravity. Then this net force equals T minus the force of gravity. Okay, so you should be able to find out that T, and it should be a bigger number than the force of gravity because tension is pulling her up and it's causing her to accelerate. Now, A and B are asking you to find out the work being done on her by the force of the helicopter and by the gravitational force. So the work for the helicopter is the work of that tension force is going to be that T times 15 meters. On the other hand, the work done by the gravitational force is going to be minus force of gravity times 15 meters. Why minus? It's because you have that cosine of phi, and gravitational force is pulling at an angle of 180 degrees from the direction where she's going. Another way to look at it is that the reason that force is negative is because it's pulling her down. It's going opposite the direction of her motion. Okay, then for part C it asks, just before she reaches the helicopter, what are her kinetic energy and speed? Well, if you want to find out the kinetic energy, I would recommend doing something like kinetic energy is going to equal the amount of work that's been put in. Because here she has 0 kinetic energy, so this is 0. The kinetic energy after all that work is done, so it would be K equals the net work done. So that's going to be basically the sum of these two. And a different way, I guess, that you could do that is with F net times m, or sorry, times 15 meters. And of course, once you have that kinetic energy, then you can go ahead, because you know her mass is 72 kilograms, you can use that K and solve for V, because it asks you for the speed. Okay, so there's quite a few parts on it, but none of the parts is terribly tough on that. Okay, now let's do a quick check. This question is trying to get you to think about positive work, negative work, and net work. It says an elevator is supported by a single cable descends on a shaft at a constant speed. Okay, so we have the force of the elevator cable has some tension. Gravitational force has some pull. But we know that these have the same size because there's no acceleration. And the object is going, the elevator is going down. And it asks us, the only forces acting on the elevator are the tension in the cable and the gravitational force. Which one of the following statements is true? Okay, it says, okay, is the work done by the tension force is 0 joules? And in fact, because you're moving downward, the force times the displacement is going to be negative. The displacement is down, the force is up. The angle between them is 180. The work done by the tension force is negative. The work done by the gravitational force is 0 joules. Again, the force done by gravitation in this case is positive because it's going in the direction of the motion of the elevator. So this has a positive force, or sorry, this does a positive work, this does a negative work, and in fact, the two of them exactly cancel out. The magnitude of the work done by the gravitational force is larger than that done by the tension force. No, they are equal. The magnitude of the work done by the tension force is larger than the magnitude of done by the gravitational force. No, they are equal, but this one is negative. This one, the tension does negative work, the gravitational force does positive work. The net work done by the two forces is 0 joules. I agree, because the work done by tension plus work done by gravity equals 0. How do I know that? Because the kinetic energy is not changing. If the kinetic energy is not changing, there's no net work. Okay, so that's just like before when we were talking about forces. If there's no net force, you can continue to move at a constant rate without acceleration. Okay, now, we've only so far talked about the simplest, easiest types of forces, which are forces that don't change as you move. On the other hand, let's think about a spring. If you have a spring, it's coiled up here, and let's pick a coordinate system where that would be x equals 0. And so at x equals 0, the spring is totally unexcited. Nothing is happening, and it's not providing any force at all. On the other hand, let's say that you squish the string. If you pull the string in this direction, in the positive, so that it's stretched out to a positive x. The force that it's going to be applying is in this negative direction because it wants to go back to this x equals 0. On the other hand, if you squish the spring like this, the force that it's going to apply is going to be in the positive x direction. So if you move the spring into the plus x, it's going to pull towards the minus x. If you move it in the minus x, it's going to pull towards the plus x. The way that you can approximate this is with what's called Hooke's law. And this says the force of the spring is going to be minus, and that's just saying it always pulls back, and it's going to be proportional to how far you stretch it. So this k we call the spring constant. And it has units of newtons per meter. You can see that right here because this is in newtons, this is in meters, so this has to be in newtons over meters for these meters to cancel out. Okay, now what does that mean physically? It means, let's say that I have K of 2 newtons per meter. That means if I stretch this out to x equals 1, I would get a force of minus 2 newtons. If I move my x to 2 meters, I would get a force, because I'm taking 2 times 1. If I have stretch it to 2 meters, I would get a force of minus 4 newtons. Okay, so what this is essentially telling me is that the further out I pull this spring, the harder back it's going to try to pull me. I mean, that's up to some breaking point where it fails, right? We can put that caveat on it. Now, so this is a very important system in physics because it's one of the systems where we can model a lot of things with springs, including things like gravitational forces, things like the electromagnetic field. So springs turn out to be a very good system to know everything there is to know about them. Now, for us, they're going to be an interesting case study because we can get them to do work. So if we have a spring and we want to, for instance, compress that spring and put a block on there, we can let the spring go then, and it will push on the block and cause the block to start moving off. Okay? And so the type of language that we're going to be introducing a little bit later on is that the spring has some potential energy when it's compressed, and as it releases, it transfers that energy to the block, and so the block at the end has some kinetic energy. So that's where we're going with this, but for the time being, let's just think about it as the spring is doing work on the block. How does that work? Okay, well let's see. The work generally would be force times distance. And notice I am going to, instead of doing this just as a f times x, I'm going to turn it into an integral because my force is itself a function of x. So that's why I've got to do an integral and split my force up into lots of little sections and add up how much force I'm getting at each one of these different x's. Now, I can easily do this because I took calculus just like you did. And so this is going to be minus kx, that's the force, times dx. Okay, so if I'm integrating now, it would be k is not a function of x, so I'm going to bring that out. Minus k times the integral of x dx from x initial to x final. And so what I would get, this integral of x would be 1/2 x squared minus kx squared over 2 from x initial to x final. Okay, so the work that is done would be minus kx, or minus, let me just try to write it like they have it, minus 1/2 k x final minus a minus 1/2 kx initial squared. Okay, and it's minus a minus, so that's a plus. So that's where we get to this equation. The work done by a spring is basically 1/2 kx initial minus 1/2 kx final. Now let's see a good example of this. So it says, in designing a spring-loaded cannon, determine the spring constant, remember that's little k, required to launch a 2-kilogram ball with an initial speed of 1.2 meters per second from a position where the spring is displaced 0.15 meters from its equilibrium position. Okay, so let's draw the picture. We've got some spring, and let's say that we compress it that x is going to be minus 0.15 meters, just in this way that I've drawn it. And we have a mass here of 2 kilograms, and initially it's not moving. And what's going to happen is that we're going to let the spring go. The spring is going to push on our mass, and it's going to launch it. And after this ball is launched, it's going to be going at a speed. So your V initial is 0, your V final is going to be 1.2 meters per second. Now, okay, what's going on here? The final velocity of your ball is going to be the initial, which is just 0, plus whatever work is put in. Okay. Now, we are assuming that the final x, when it gets launched, it's going to get launched at x equals 0. So we can forget about that term. And the initial term is this 1/2 k initial, kx initial squared. This is the amount of energy that it's going to transfer over into the ball. Okay? So I'm essentially going to say my 1/2, my final kinetic energy of the ball equals the work that's going to be done on it by the spring. Okay? So that's 1/2 m v final squared equals 1/2 k x squared. So you know the mass of the ball, you know the final velocity of the ball, you know the x that the spring was squished down to, and what you want to find is k. And k, remember, is going to be some number in newtons over meters. Okay, so I'll let you do it. I think you're going to find out something that it's something close to this. The key thing, there's a couple key things to notice here. Don't get confused because in this chapter they use a capital K and a lowercase k. Capital K is, that's your 1/2 mv squared. Lowercase k is some number in newtons per meter. K is this, so this is a spring constant. This is the kinetic energy. They don't have a real relationship with one another. They're two different things. They just happen to have sort of similar notation. So be aware of that. Okay, so in fact, that's all we're going to do today. When I planned this lesson, I expected for us to do power as well. And if you look in your PowerPoint for today, I include some of that stuff. But I did not go over it in class today, so I won't cover it right now. But what's the main takeaways? Work can be positive if you're going in the same direction as if the force on the object is in the same direction of its motion, or negative if the force on the object is opposite the direction of its motion. Positive work increases the speed of an object. Negative work decreases its speed. And when work is applied by a variable force, an integral must be used. This is not, just a sec. Okay, I'm back. I'm sorry. I accidentally skipped to the end of the lecture and I allowed myself to think, I guess we're done. We're not done. So the spring forces are just one example of forces that vary in space. In fact, all of the intermolecular forces are forces that vary in space, like for instance, the Coulomb force between two charges. Or the gravitational force, in fact. If you go out at far enough distances, you can notice it varying in space as well. So, what we will be interested in general is to find the forces that are done by by forces that are varying in space, and it's going to be the exact same process as we did here, where we put in the force and we integrate. but it could be any old force that's a function of x. Now, it might not be obvious to you that this will still work. Why would it be that you would still be able to use your work energy theorem, which you might remember from Friday's video? We did that in a way assuming that the acceleration was constant. So let's not do that now. Let's quickly show that we don't need to make that assumption. So the work is going to be the integral from x initial to x final of the force times the distance. Okay? And this force is varying with respect to time, but we know, or sorry, with respect to displacement. And what we can do is realize that if we are dealing with Newton's second law, F equals ma, so I'm going to use that, x initial to x final. I'm going to write this as m. And now I have a as a function of x dx. What is a? Well, what a is so x initial times x final. It's going to be dv as a function of x dt times dx. And the next argument that we make is, well, what if we changed the variables within our integral to be from initial position to final position to initial velocity to final velocity? What you would do then is that this is dx dt. I'm going to keep this dv around. I'm going to change my integral over to be an integral over the speed, or rather the velocity. And now this dx dt is in fact v. So this is m v dv. dx dt is v. Okay, now I go ahead and I do that integral, and I get 1/2 mv squared integrated from v initial to v final, which is in fact just 1/2 mv initial, or sorry, v final squared minus 1/2 mv initial squared. Okay, so what have we done? We showed that this work energy theorem it's valid even if the force is a function of x. So it doesn't need to be a constant force for this trick to work. So this can be super useful. Let's just look at a sort of a simple example. It says a 12,500 kilogram truck, so a big boy. Is accelerated from rest by a net force that decreases linearly with the distance traveled. Okay, so look at this this image. It says that if we are drawing this out, this looks like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 13 kilonewtons would be 13,000 newtons, and over the course of 150 meters, it's going down to a force of 0. So this force is always pushing forward. You know it's forward because it's positive. Positive forces are pushing in the plus x direction. And it asks you to find, using the information provided and work energy methods, determine the approximate speed of the truck when the force is removed. Okay, so here the force is removed. How fast has it gone by having all of that push? Well, what you're going to do here is find the amount of work that's being put in, and then realize that if you started out with an initial speed of 0, you can use that to find the final speed. Okay, so let's think about it. How would we find the work in this situation? Well, if this is our force versus x, the integral is essentially going to just be the area under the curve. Okay, so in this case our work would be 1/2 times 13,000 newtons times 150 meters. Okay, so that's your work, and then if you wanted to go ahead and find out what the speed was at the end, you would go 1/2 m, where we know the mass, v squared equals w. So your v would be, take it times 2, divide by m, 2w over m, and stick in numbers and you should get something right around here. Okay, so that's a nice, easy, quick example that uses this method. Let's take a look at one of your homework problems that's a little trickier. This one says, you've got the force on a particle directed along x-axis, and it's given by this expression. So I'm going to write that out. F equals F naught over x times x minus F naught. So you notice this is in y equals mx plus b type of notation, and it asks you to find the work on the force done by the force in moving the particle from x equals 0 to x equals 2 x naught, first by plotting x and measuring the work by the graph, and then also by integrating f. Okay, so let's try to draw this. Here's your x, here's your f. If I'm comparing this to my y equals mx plus b form, it looks to me like the intercept of this graph is going to be minus f naught. When I put in x equals 0, f is going to be equal to minus f naught. Now, it asks me to go over to x equals 2x naught. So there's 2x naught, there's x naught. In this case, my slope is going to be rise over run. So if I'm going up f naught over x naught, there I go, up f naught over x naught, there I go. All right, so that's my force versus distance plot. Now, thinking about this physically, what does it mean? What it means is that I'm being pulled backwards until I reach the position x naught, and then I'm going to be pushed forward by this force until I reach x 2x naught. However, if I'm looking at this as an integral of this function, as an integral of f versus dx, what I would be looking at is this area plus this area. Now, it's pretty obvious that this area right there and that area right there are going to be equal, but this would count as a negative area because it's underneath the axis, and this would count as a positive area, so the total work is 0. Interesting. Why is that? Well, it's because part of the way the force is pulling backwards, that's negative work. Part of the way it's pushing forwards, that's positive work. Now, how else could you find that? Well, you could also find that from part B. So this is all part A. And then part B, if you go ahead and do the integral of from 0 to 2x naught of f naught times x over x naught minus 1 dx. Okay, so I'm going to let you try to do that integral and make sure that it also gives you a work of 0 joules. All right, I believe you can do it. All right, so that is in fact all that we're going to do today, because we ran out of time to get to power. Power is the amount of work being applied to a system divided by the amount of time, and it has units of joules per second, which is called a watt. And so we'll do more problems with this. So what I would recommend that you do for today is try to get as many of the Chapter 7 homework problems as you can done. And as I've said before, there's quite a few problems on this homework set. So if you leave them all for next Saturday night, you are going to maybe crash and burn. So please get going. I've given it so that you have about 6 homework problems per lecture. So I think you can get it done. Good luck, and thank you for watching.